These are the notes on dilutions and the introduction to phase changes that we went over in class today. This is part 1 of 2 videos. So we've talked about how we express concentration and molarity and molality. Um, the next topic is how we would calculate the amount of a stock solution to use in order to dilute a solution to a lesser concentration. So sometimes we do need to take a highly concentrated solution such as 13 molar hydrochloric acid and dilute it to a much weaker concentration, say like 1 molar. And so we use this equation, it's called the dilution equation, to assist us in doing that. The equation looks like this. M1 times V1 equals M2 times V2, where M is your molarity of the initial and the volume of that stock solution you would want to use. And then M2 would be the new concentration that you're trying to dilute it to, and then the volume of the final solution, V2. Now, sometimes you see this formula written instead of M1 V1 equals M2 V2. You see it as C1 times V1 equals C2 times V2, where C just means concentration. In this case, since molarity is our most common unit of concentration, we use M's usually. The volume in this case could be in liters or milliliters as long as they match so that they would cancel out. So let's look at an example. So a prime example of a calculation or problem you would have like this would be one like we see here. It says you have a 12 molar solution of hydrochloric acid in the stockroom. You need 500 milliliters of a 0.6 molar solution. How much of the 12 molar solution would you use? All right, so as you identify your givens, 12 molar is the initial, we'll call that M1, and you want to know how much of the 12 molar should you use. So we're actually trying to figure out V1 in this case because you want how much of the 12 molar. The V2 is 500 milliliters, and the concentration you're trying to dilute it to is only 0.6 molar, so they'll be your 2's. So substituting into the formula, 12 molar times X equals 0.6 molar times 500. Now you could convert the 500 milliliters to liters. If you did, your answer would just come out in liters. It's fine to leave it in milliliters as long as you're aware of your units. As you rearrange the equation, notice the molarities do divide out, so you multiply 0.60 times 500 and then divide by 12. That'll give you 25 milliliters for that answer. All right. The next thing in our race to the finish unit that I would like to address are the phase diagrams and the heating curves. These are two important graphs that represent the changes in states of matter. Sometimes it will be water you're dealing with as your substance, but it could be other substances like carbon dioxide or methane gas. It could be any substance. So always pay attention to what's being graphed. Now, before we look at the diagrams, let's review the changes of state. So when a solid changes to a gas directly without ever passing through the liquid state, this is something that you see like at Halloween time, like when you see the witches' kettles, they put the carbon dioxide, they call it dry ice, it's solid carbon dioxide, and it goes directly to the vapor state. And so that phase change is referred to as sublimation. So sublimation is one probably that some of you have not heard of before, or if you have, you just don't hear of it often. But sublimation is one of our phase changes. It's when the solid changes directly to a gas without ever passing through the liquid phase. The next phase change is solid changes to liquid. Can you guess what that's called? That's one you should all be familiar with. Hopefully you said that that would be melting, when a solid changes directly to a liquid, like when solid ice melts. Solid excuse me, liquid changing directly to a solid. So this is the opposite of number 2. So liquid changes to solid, so water freezes. That's right, freezes. Liquid changing to a gas. So when a liquid changes to the vapor state, that is called evaporation or vaporization. Evaporation or vaporization. The opposite of that process, gas changing back to a liquid, we refer to that as condensation. Condensation. All of these phase changes do involve energy changes, and I'll remind you of that in just a few minutes when we finish with the review of these um, changes of state. All right, so number 6, gas changing back to a solid without ever passing through the liquid state. So this is the opposite of the first one. So the first one, solid to gas, was sublimation. And this next one, gas changing directly to a solid but without ever liquefying, this is probably one that very few of you have heard of for sure. It's called deposition. The root word there is deposit. Think of it as it deposits from a gas to a crystal or a solid. That's what's happening here in this diagram. We have sublimation and deposition occurring here because in the bottom of this flask we have some solid iodine crystals. And without liquefying, if you heat it just a little bit, you'll have this pretty purple vapor that forms. And so it's subliming. So here's your solid down here. And then up in here is your gas. It's changing directly to the gas. Now, as it hits the cool lid here, it starts solidifying again. So this is the gas changing back to a solid up top. And so this is the deposition as it kind of collects up on the top as little purple crystals of iodine. That's called deposition. Now remember from our second unit when we first were introduced to energy, I shared with y'all a little memory device that even included the plasma state. And we're not dealing with plasma state here, we're just dealing with the first 3. But what I told you is anytime you're going from the solid state towards the vapor state, that's always going to involve an absorption of energy. So these are always endothermic processes. And anytime you're coming backwards or towards the solid or the less energized state, because remember solid particles are vibrating in fixed positions that have the lowest kinetic energy, that's going to have to release energy to come back. So these are always exothermic processes. 2 things you also need to be aware of as far as terminology goes is when you see the word normal written in front of boiling point or in front of the word freezing point, that is a specific set of conditions. And what that means is that that's the boiling or freezing point at 1 atmosphere of pressure. So that's like your standard boiling point. But if that's a normal boiling point, normal freezing point, it's going to be at 1, it's occurring at 1 atmosphere of pressure. And that will be important for these diagrams that we're going to be looking at in our next video lesson. Again, this is iodine undergoing sublimation. In the next video lesson, I'm going to introduce you to the phase diagram.